All right, so welcome back. Like I was just saying before I hit record, this is very important, and the key to this section, and this is something that will be very important for anybody moving into chemistry 2 or chemistry 3, is this concept of intermolecular forces. Even some of you might be environmental health and safety students. I usually teach the environmental course. Environmental chemistry is, I've been the only one that has been teaching it for like 5 years. So this is actually something we talk about in that course as well, this concept of intermolecular forces. These forces relate to a lot of properties, specifically like hydrogen bonding can control things like density of water. But in this course, all we care about is the melting and boiling points. So for the purpose of today, just assume melting and boiling point are the same. And I mean, I know they're not, but what I mean is if you have a strong intermolecular force, you're going to raise the melting point. And if I say melting point, I also mean boiling point. And if I say boiling point, I mean melting point. There, no matter what, if we increase intermolecular forces, the forces between different molecules, they're harder to break apart, to get excited, to move around with kinetic energy, meaning it takes more energy to boil them or melt them. So we already did ionic bonding. We'll talk a little bit more about that at the end of today. I have a really good practice example for us. But the three we're going to look at today, and we're going to do all three of them because I did it with the class this morning, so we kind of have to. And it will be a really good place to end for the week, is London dispersion, dipole-dipole, and hydrogen bonding. Now, while I have you all here, there's a lot of you here, just a reminder, and I'll be posting this on D2L. You might have gotten an email this week or today. You guys have tomorrow off, the whole campus, well, all of the students. So students have no classes tomorrow. You have a long weekend. You guys are lucky. I do not have a long weekend. I have to go into work and do a bunch of things. We're having meetings and all sorts of things. So this for you guys will be the last class this week. So yeah, no classes, no labs, nothing tomorrow. You have a long weekend. You're so lucky. Anyways, point that I'm trying to make is I want to finish this today, these three topics, because it's a really good place to end this week. All right, so the first of three. Now, I can explain all three forces in under 1 minute. So what I'm going to do is I'm going to, in great detail, explain all three of them, and then I will tell you in 1 minute how to kind of figure out the differences between the three. So I'll give you the long version, and then I'll give you like the quick and easy version. So the long version, it's not that long either. Oh, 1 second, guys. I got a phone call, and I think it's my water people. Okay, I'm back. That was, I get water delivered every Wednesday. So anyways, okay, I have water now. So London dispersion forces. London dispersion forces are the easiest of all the forces. And let me just start by telling you the easy answer. Every molecule has London dispersion forces. So basically, when you guys do this question on a quiz or a test or the final, and I will ask you, what are the intermolecular forces in these molecules? Every single molecule has London dispersion. So what is it? London dispersion can be simply explained by being like a very weak dipole-dipole force. Now, what do I mean by dipole-dipole? I mean like polar. Remember yesterday or the day before, we talked about polar molecules? Well, London dispersion is like a weak version of that. It's not quite polar, but it does form a temporary dipole. Now, a temporary dipole means it's not permanent. And the reason that happens is because in every molecule, the electrons are moving rapidly. They're orbiting, they're circling the atoms around the bonds. And sometimes the electrons can kind of move on one side of the compound and make a negative charge. And that means the other side of the compound has a positive charge. So you get a very weak force. This is the weakest of all the forces. Again, it's very much related to polarity, but just a lot weaker. So not every molecule is polar. We saw that yesterday or the day before. But every molecule does have this force. And again, it's very weak. Now, there's one problem with this. Sometimes you guys will have a list of molecules where I'm going to say that they tie. And what I mean is you have so much information about the intermolecular forces that they seem to have the same. And when that happens, what you can do is look at the London dispersion and count the number of electrons. There are two factors that affect the amount of London dispersion forces. And the first, and really the only one for you guys, is the number of electrons. The more electrons something has, the more London dispersion forces it has. And I kind of skipped over this, but the more London dispersion forces a molecule has, the higher the boiling point will be. So what about this guy on the bottom? Well, this is something you'll look more at if you have me in 24, or well, not me, but if you are in chemistry 3 or chemical engineering, this what you'll look at a little later. Some molecules can be long and flat, like hydrocarbon chains. You don't have to worry about this for 1120. We're not dealing with long, flat hydrocarbon chains. We're dealing with very small molecules. Okay, so what am I talking about? Let's put this all together. Oh, sorry, and this slide shouldn't be here. So let me explain. It's not that it shouldn't be there, but this slide says this again. So again, electrons, the more total electrons in a molecule, the stronger the London dispersion force. So this slide, I mean, it's very important, but it doesn't say anything new. It's just like a summary of the previous slide. Oh, okay, I kind of forgot that slide was in there. I meant to get rid of it, but anyways. Okay, let's do this. And at the end of today's class, guys, we're gonna put all of this together. It should make sense. The group this morning didn't have much trouble, a couple questions. All right, so imagine I'm asking you on a quiz or something, multiple choice, or true or false, fill in the blank, I don't know what, but I might say, which element here of these two has the highest boiling point? Or, more specifically, which of these has the higher London dispersion? Well, every one of these has London dispersion. LDF, London dispersion forces. The question is, which of them have higher ones? So what we need to do is exactly like Aman says in the chat, we need to see the electrons. Well, where can I find electrons? Well, I can find electrons on my most favoritist thing in the world, my periodic table, which I'm trying to share with you now. But my computer is being silly goose. Okay, let's share it like this. All right. So in that question, we were looking at N2 versus F2. So, okay, N2, F2. Well, I mean, this is pretty easy. N2 has 14 electrons, right? I'm multiplying it by 2 because I have 2 nitrogens. So 7 times 2 is 0.2. Or, oh my gosh, so sorry, my brain is not working here. 7 times 2 is 14. Okay, well, what's 9 times 2? 9 times 2 is 18 electrons. So nitrogen N2 would bring together 14 electrons. Fluorine would bring together 18 electrons. So that means, I'll go back to my PowerPoint, fluorine has 18 electrons, nitrogen has 14 electrons, F2 is higher. All right, now that's pretty easy. It can get a little more challenging though, because look at these two. I have SO2 and CS2. So let's have a look at this. Let me erase the board or my table here. So I have C, S, and O. I've already forgotten what the chemicals are. SO2 or CS2. So SO2 or CS2. So I'm going to ask you guys right now in the chat, which element has more sorry, not element, which molecule, which molecule has more electrons? Which total molecule has more total electrons? You guys tell me in the chat. Okay, you got 50-50 if you don't know, SO2 or CS2, which one? Yeah, oh man, Abdul Halim even puts in the greater than or sign. That's amazing. I'm getting all good answers here in the chat. That's awesome. Perfect. This morning I had a couple of students that said SO2, but again, when we count the electrons, and like Abdul Halim in the chat puts the numbers there. If this was on a test or something, you don't even need to calculate it if you don't want to, as long as you can tell me, or you know, as long as you know which has the most electrons. So Naval, Hamna, everybody, I'm getting tons of private messages too. You all are correct. Okay. For anybody in class who isn't sure why, well, SO2, if I add together 16 electrons from the sulfur, and I add 2 times 8 electrons from the oxygen, you will get a total of 32 electrons. Sorry that it's a little messy there. I don't have a lot of room to write. Okay, well, CS2 is 6 electrons, but I'm going to add to that 2 times sulfur, which is 16 electrons. So that's 32 plus 6, that's 38 electrons. Now, again, you don't need to show me that on a test. If you can like see with your own eyes that CS2 would have more electrons, you don't have to write that. You just circle CS2. Calcium carbon disulfide. And if I asked you to explain why, you would just have to say, well, it has more electrons. So this has 32 electrons. This has 38 electrons. So, oops, CS2 is higher. All right, we have 1 down, 2 to go, and the next 2 are easy. The next 2 have a little bit more complicated definitions, but they don't have any calculations in them. So for the next 2, you just have to remember a couple of things. And the good news, I do have good news, believe it or not, we've already done this. Dipole-dipole forces, our second of the 3 intermolecular forces for covalent compounds, these are in polar molecules. If the molecule is polar, it has dipole-dipole interactions. So you might be thinking, what is the difference between London dispersion and dipole-dipole? Well, London dispersion is temporary. The electrons are moving around and little tiny dipoles can form. And remember, when I say dipole, I mean a positive and a negative end, like a magnet. A polar compound has such a difference in electronegativity in the compound or in the molecule, the dipole is permanent. It always has a negative end and always has a positive end. So this is stronger than London dispersion. Now, I don't have much to say here because we already did this, but I did this for the class this morning, so I'll do this for you guys as well. Just a reminder. Okay, when we want to see if something has dipole-dipole forces. Oops, I gotta write that again, this dumb pen. All right. So to figure out if something is polar, because that's all we're doing here, okay? And I'm not looking for polar bonds, I'm looking for polar molecules. We ask ourselves 3 questions. Are there more than 3 different elements? Okay, so question number 2. Does the central atom have a lone pair? Lone pair or lone pairs plural. Okay, and then 3, if there's no central atom, so for example, 2 elements, I shouldn't say 2 elements, but I'm going to get rid of that. That's not a good thing to say. No central atom would be like literally 2 atoms bonded together. Okay, so just like H2 or HF. Are they different? Oh, this pen. All right, so let's keep these questions in mind. Now, if anybody hasn't seen this, it was in class yesterday. I'll be putting your PowerPoints up, or your YouTube videos up to date today or tomorrow. Again, I'll be at work all day tomorrow, so I can kind of update my YouTube. But if you didn't see this before, if you've never seen this, it'll be uploaded on YouTube. We did this, I think, yesterday or on Monday. Anyways, let's go through these 3 and ask ourselves these questions. So H2, are there more than 3 different elements? No. Number 2, does the central atom have a lone pair? There is no central atom in H2. So I go down to question 3. If there's no central atom, are they different? Are the elements different? The answer is no. So it's non-polar. What I mean is the answer to all of my questions, every question, is no, so it's not polar. If the answer to any of these questions is yes, then it's polar. Okay, so question number, let's go to methane, CH4. Are there more than 3 different elements? No. I'm going quick through this because we've done this before, by the way, so I'm not really asking you guys to do these for me because we've already done all of these. Anyways, so CH4. Are there more than 3 different elements? No. Does the central atom have a lone pair? No. Methane, by the way, looks like this. So the central atom has no lone pairs. And question 3 doesn't apply. Question 3 is only if there is no central atom. There is definitely a central atom here. So the answer to all of these questions is no, it's non-polar. All right, I got some stuff going on in the chat here. Oh, I got some answers. Iman and Abdulhalim, you guys are perfectly correct. No, the answer is no, no, yes. So good old H2O, maybe my favorite element of all time. Okay, well, definitely one of the most important. H2O, and you really want to make sure you know how to do this, would look like this. Okay, and again, I can't review this much more. If any of you have questions after class, like you don't know how to draw electron dot diagrams or something, you can stay after class. But we've drawn this 50 times. Let's go through the questions. More than 3 elements? No. Number 2, does the central atom have lone pairs? Absolutely. This central atom has 2 lone pairs. Oxygen is the atom that all of the other atoms are bonded to. Okay, so we get the answer yes. I didn't mean to write it like that, but here we are. So this is polar. Cool. So what that means is, if I was going to write this down, H2 has London dispersion. CH4 has London dispersion. Everything has London dispersion. H2O has London dispersion. But you know what H2O also has? Dipole, dipole. Now that looks like a P, doesn't it? D, there we go. Now, think about these 3 molecules, hydrogen, methane, and water. Which one of these do you guys think would have the highest boiling point? This is a good multiple choice, right? Like, take these elements, which would have the highest boiling point? What do you guys think? Hydrogen, methane, water. Yeah, I got one answer from Franz. Anybody else? I won't say what's right yet. I'll get a couple more answers. What do you think? Highest boiling point. Let me give you a hint too. The more, I'm not getting a lot of answers, so there might be confusion. The more intermolecular forces you have, the higher the boiling point. So hydrogen and methane have London dispersion only. Water has dipole-dipole as well. Okay, now I'm getting some answers. So Abdulhalim, Shadan, Humna, everybody, you're all correct. For a question like this, guys, you do not need to worry about the number of electrons. The minute you see dipole-dipole, that wins. Dipole-dipole is much stronger than London dispersion. So maybe some of you guys were taking the time to start counting electrons. If you see dipole-dipole there, it beats London dispersion. It's kind of like poker. I don't know if you guys play a lot of cards. I mean, when I started teaching 10 or 11 years ago, everybody I knew was playing online poker. And you can think of this like a poker hand, you know, a pair would be one of a kind, or 3 of a kind would be a pair. And intermolecular forces are like that. If you have 1, that's okay, but 2 will always win. 3 is even better, okay? Which brings me to our last and final, well, not my favorite, but one of the most interesting intermolecular forces, hydrogen bonding. And yeah, Aman mentions LDF, London dispersion, is the weakest. So the minute you see dipole-dipole, you know you have something better, something, I guess better is not the right word, but something higher. Okay, guys, I will admit I'm not really happy with a couple slides here. One slide in particular we can totally get rid of. I don't know why I kept it in there, but anyways, this is pretty easy. Hydrogen bonding is our 3rd and last intermolecular force. This is very similar to dipole-dipole. I mean, they're all dipole attractions. The difference is London dispersion, incredibly weak dipole attraction. Polarity is a good normal dipole-dipole attraction. And hydrogen bonding is when you see a dipole-dipole attraction like turned up to maximum. It is like the strongest dipole-dipole attraction you can have. This is because of the electronegativities. We won't get into that. All you need to know is that hydrogen bonding happens when you have hydrogen bonded to F, O, or N. Okay, so it's like fun is how I always remember it, or I guess it would be fun. It wouldn't really be fun, but F-O-N, F-O-N. Say it to yourself. It's fun, F-O-N. Hydrogen bonding is when hydrogen is touching an F, an O, or an N. Okay, so we're going to put all of this together in a minute. One disclaimer I will mention is hydrogen bonding only happens when the hydrogen is literally bonded to F, O, or N. So if a molecule has hydrogen in it, it doesn't necessarily mean it's hydrogen bonding. The bond actually has to be attached to, and you'll see this in a few minutes, F, O, oops, or N. Okay, so this slide has a lot of things packed into it. Yeah, so like Aman says in the chat, like CH4, okay? CH4 has 4 hydrogens, but that doesn't have hydrogen bonding because those hydrogens are not attached to F, O, or N. Yeah, exactly. So just because it has hydrogen doesn't mean hydrogen bonding. So you guys got to remember F-O-N, F-O-N. All right, now this slide, beautiful slide. Love this slide, so interesting. Every one of these molecules has London dispersion. Oops, sorry. Okay, so London dispersion, London, this pen. London, London dispersion, London dispersion, London dispersion. They all have London dispersion. All of these, by the way, also have dipole-dipole because they're all elements bonded together that are different. So these also have dipole-dipole, 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 and dipole-dipole. Now, let's forget about hydrogen bonding for 1 minute. Remember that I told you if you had a tie with London dispersion, that you could count the number of electrons, and the number of electrons will tell you which has the higher boiling point. So, okay, HF, 10 electrons, the boiling point is 19.4 degrees Celsius. Not a lot, but I mean, look what's going to happen in a second. Hydrochloric acid has 18 electrons. That boiling point is negative 84. So something weird is happening right now because I have just increased my number of electrons, but the boiling point dropped. That should not happen using our earlier discussion, London dispersion wise. This all makes sense though. Notice as you increase electrons, the boiling point gets higher. This totally makes sense. So what is going on with hydrogen fluoride, HF? For some reason, hydrogen fluoride has the smallest number of electrons, but the biggest boiling point by far. And the answer is good old hydrogen bonding. It's the only one in this list that has hydrogen bonded to F, O, or N. So it has a really big boiling point. So yeah, as Abdul Halim says in the chat, it has a hydrogen bond. Again, think of this like a video game or a card game. The more items you have, the better hand you have in a card game, the better it is. And HF has the ultimate. It has all 3. It has everything, right? Think about playing a video game. If you need to do 3 objectives and these guys only have 2, they're not going to be as good. So hydrogen bonding really helps raise this boiling point. Okay, this slide, guys, shouldn't be in there. Get rid of it. Don't worry about it. I didn't mean to put it in there. Don't even look at it. Pretend it never existed. So I would like to do with you guys 3 more slides and we are done. It's only 3:05. Right, yeah, so I'm just laughing at the chat there. So yeah, it's 3:05. I only want to do 3 more slides. So let's slow it down a little bit. Let's do one at a time. This one, I'm going to warn you, question C is hard. For C, you might want to draw the shape. Okay, sorry. All right, but let's look at the easy ones. I mean, it can't get much more easier than A and B. The question is, which of these molecules have hydrogen bonding? Okay, well, A. A cannot, I got a message in the chat. Let me read that before I answer. All right, Iman has the answers there for us already. So yeah, A cannot have hydrogen bonding. No. Like, think about how easy it is. A doesn't have F, doesn't have O, doesn't have N, not possible. All right, B. This is the easiest one. I mean, this, if you see this on a test, it'd be like a gift to you. This is a yes. And the reason is because the molecule HF looks like this. So it's a hydrogen bonded to a fluorine. Everybody's happy. This one on the bottom is tricky because what you have to ask yourself when you're looking at question C is, are those hydrogens bonded to the oxygen or are those hydrogens bonded to the carbon? And again, that's how specific you need to be. The hydrogen, it can't even be in the same molecule as F, O, or N. It has to be literally bonded to it, exactly bonded to it. So this is a good little question here. Naval and Abdulhalim and Iman all have the answer perfectly. The H is not bonded to the O. It's actually bonded to the carbon. How do they know that? Well, review time. And I don't mind reviewing this because we've never done this question before. I think this is formaldehyde. Yeah, this chemical, guys, is called formaldehyde. You might have heard of it before. Formaldehyde is a chemical compound that's used to preserve things. So if you've ever walked into a biology lab and there would be like a brain or a human heart in a bottle, in the old times, it would typically be preserved in formaldehyde. You might have seen this in old movies, like old horror movies. You see like them talking about formaldehyde. All right, it's a good time of year for scary movies. So if you've ever seen, like I said, in an old movie, like some mad scientist has like a brain in a jar, it's probably put in for formaldehyde. I think it's quite poisonous. Not good for us, but it preserves things very well. All right, so think about this as a puzzle, guys. I have a carbon here that has 4 single lonely electrons, but I also have 2 hydrogens that have single lonely electrons. So why don't they pair up? They could be friends. So this guy and this guy pair up, that's good. Everybody's happy there. Poor old carbon, though, is still missing 2 electrons, well, or still needs 2 partners, 2 electrons. But look how convenient this is. The oxygen also has 2. So when I put this together as a molecule, I will get a double bond. I'll even draw it like a double bond. So I get a double bond to the oxygen and 2 hydrogens sticking off. I'm drawing it like that, guys, because the shape is trigonal planar, but we don't need to worry about shapes today. Shapes have nothing to do with this. The hydrogen, as somebody said in the chat, maybe Naval or Abdul Halim, hydrogen is bonded to the carbon, not the hydrogen. So no hydrogen bonding. All right, that was a tough one, guys. That is not the easiest one. Actually, in my opinion, that's one of the hardest ones. Yeah, I mean, you could totally feel bad for this molecule because it's like, it's so close. It could have hydrogen bonding, but it doesn't. Formaldehyde, really? I have formaldehyde brought up on my other screen here. I don't know if I have any other facts of it. It's very dangerous to humans. It's a carcinogen, so cancer causing. Um, Anyways, there's some fun facts about formaldehyde. Okay. All right, two more slides and we're done. I'm going a little slow and I'm going a little longer, but I really like, it would be stupid of me not to finish it here because now we can put all of this together. So two slides left. First things first, this, I'm gonna wink. I know you can't see me, but I'm winking right now. This is a test and final exam question for sure. You, now not this slide, but this topic. I will give you a couple of molecules or compounds, and I will say which has the highest boiling point. That's it. This is your cheat sheet right here. Remember I said at the beginning of class, I could explain this in under a minute. Well, here we go. Let me just write this word. Okay. How can I explain all of these forces in under 1 minute? First, ionic bonding is not sharing electrons. Ionic bonding is the strongest ultimate intermolecular force. Ionic bonding is number one. If you see an ionic compound, it has the highest. All right, the bottom three. These bottom three are for covalent compounds. So how do you figure it out? First, you look for a hydrogen bond. Hydrogen bonding is when H is bonded to F, O, or N. Next, you look for dipole-dipole forces. That's the third strongest. It's dipole-dipole if it's polar. And number four, if you don't have anything, you look for London dispersion. Every molecule has London dispersion. And if it comes down to London dispersion, you check the total number of electrons. That might have been a minute and a half. I don't know. But there you go. That's my rundown. So Iman, this is a great question because this leads me into the next and final slide. If you guys aren't following your chat or you're not looking at your chat, there's a question in there from Iman. What about MgO, magnesium, that's a metal, oxide? Would magnesium oxide be higher than HF? Well, magnesium oxide is ionic because it's a metal and a nonmetal. HF is obviously covalent. There's no metal there. And it has hydrogen bonding. It has all three forces. But ionic will always win. Ionic is in like a game of poker is like a straight flush. I don't know if you guys know what that means. I don't know if you guys play poker. But it's the best. That's all I can say is ionic is number one. Ionic will be higher. Now, we could get a little bit more complicated, like what if I asked you to compare two ionic compounds, but excuse me, that's not in this course. When you're looking at ionic compounds, you have to look at things like their formal charges. It's a little bit more in detail than we need to be in this course. So I would never get you to compare two ionic compounds. It would be more of like, I would slip one in like question A here. Question A is a good example. So A, B, C. Now, how about this, guys? We're very low on time because it's 3:15. Oh, I don't know what I want to do. Okay, I will give you guys, and I don't have much time. I'm going to have to rush you a little bit because you might have class after this. Why don't you take 2 or 3 minutes and just see if you can circle or guess the highest compound, like whatever you think it is. Okay, if you don't know, see if you can make an educated guess. And I will be back in 2 minutes to check your answers. Again, if you have no idea, maybe you don't have your periodic table, see if you can make a guess. All right, and I'll be back in 2 minutes and we'll do the answers and then halas. All right, so I'll mute myself and be right back. Okay, so I'm recording again. I just kind of forgot to hit record there, but we had some really good answers in the chat. Actually, a lot more correct answers than I had this morning. And you know, this could be a very quick question in some situations. I think A and C are extremely quick, but now I've been doing this for a long time too. But okay, look at A. Sodium, that's a metal, sodium chloride or iodine. Don't even, the minute you see an ionic compound, don't even think about London dispersion. Don't think about electrons or dipole. Don't worry. This wins. It wins because NaCl is ionic. All right, well, okay. Now I'm going to skip B because B is the one where we have to do a little bit of work. Let's look down here. We have NH3. Now, guys, I can promise you that in NH3, the hydrogens are bonded to N. pH3 looks the exact same. You guys practice this enough, you could draw Lewis or electron dot diagrams in your sleep, I promise you. Now, I know I've been doing it for a while, but I mean, they're so repetitive. So NH3 wins. Why does NH3 win? NH3 has all the intermolecular forces, but more specifically, NH3 has hydrogen bonding. This pen. pH3 does not. All right, this one in the middle, I'm gonna like separate it now. This one in the middle has a challenge. IF and IBr are both polar. Now there's no hydrogen bonding, they are not ionic. So they definitely both have dipole forces. But they also have London dispersion forces. So this, if you were playing a video game or a card game, you know, and I showed up and I said, oh, I got dipole and London dispersion. And you said, oh, well, I have dipole and London dispersion. Well, then we need a tiebreaker. And how do we break a tie? We look at the number of electrons. So IF has, I gotta open up my periodic table. I'm gonna do it on my other screen here because we're very low on time. I should know what I is, I'm embarrassed. I is 53. So guys, I has 53 electrons. F has 9. Br has 35. So think about it. Both of these have 53 electrons from the iodine, but the IF total has 62 electrons total. The IBR has 53 and 35, 88 electrons total. So IBR wins. IBR has more electrons. Again, we had a problem. We had a tie. We had dipole, and London dispersion. How do you break a tiebreaker in this topic? You add the electrons. If you ever have a tie where they have all of the intermolecular forces and you don't know, then you move to number of electrons. That, I'm pretty sure that's mostly true. I mean, there's always exceptions in chemistry, but this is about, you know, a generalization for the majority of molecules. Okay, I'm gone way over time, guys. I'm sorry. Well, I'm gone 4 minutes over time. I'm gonna stop talking. I am done work for today. So if you guys have any questions, you need any help, you want me to show you anything, you can stick around, but I'm gonna stop the YouTube video now. And you know, wish you guys a happy weekend. You guys, you can have a long weekend. You don't have school tomorrow. So enjoy your long weekend, and I'll see you next week.